Welcome back, everyone. Today we get to play with partial fractions in section 8.5. So this first example, I'm going to show you how to do it without partial fractions and how to do it with partial fractions, and hopefully motivate why you really want to learn partial fractions. So we'll look at 50 dx over x squared plus 6x minus 16. So up to this stage, our only option is a little bit of trig substitution. So I'll go ahead and grab that 50 and we'll complete the square. X squared plus 6x. I'll move the minus 16 over a bit. So completing the square, leading coefficient of 1 already, so half of 6 is 3, 3 squared is 9, so I'll do a plus 9 and minus 9. That way we've added 0. So we changed the look, but we didn't change the value. So we have integral of dx over x plus 3 quantity squared minus 25. So this is of the form u squared minus a squared. So we'll use x plus 3 u as our a secant theta, 5 secant of theta. So dx, even if we think of moving the 3 over here, derivative of a constant is 0. And derivative of a secant is secant tangent. So dx is 5 secant theta tangent theta d theta. Okay, plugging and chugging. 50 is still camped out front here. dx is replaced with 5 secant theta tangent theta d theta. Downstairs, x plus 3 was 5 secant theta, so x plus 3 quantity squared would be 25 secant squared theta. And let's see, then we had a minus 25. All right, so a little bit of factoring. I can pull a 25 from the bottom, a 5 from the top. Do a little reducing there in a moment. So we have secant theta, tan theta, d theta. And then downstairs, after we've factored the 25, we have secant squared theta minus 1. Hopefully you remember your trig identities. That is tangent squared theta. So 50 25ths is 2, 2 by 5 is 10. So we've got a 10 camped outside, 10 integral of secant theta tangent theta d theta over tangent squared theta. And a little bit more canceling out. One set of the tangent thetas will drop, bringing us to 10 integral of secant theta d theta over tangent theta. After that, we can go to sines and cosines, do a little bit of canceling. So 10 integral of secant is 1 over cosine. We're dividing by tangent, which means multiplying by cotangent, which is cosine over sine. So then we have 10 integral of cosecant theta d theta. So then we can use from the tables, integral of cosecant u du is minus natural log absolute value of cosecant u plus cotangent u plus c. So we have negative 10 natural log absolute value of cosecant theta plus cotangent theta close it up, plus c. The original was in terms of x, not theta. So here's where our triangle comes in handy. So our substitution line over here, I'll reorder it a little bit and call it x plus 3 over 5 is secant theta. That'll let me draw a nice pretty triangle here. So there's our right angle, there's our friend theta. Secant is the reciprocal of cosine. Cosine is adjacent over hypotenuse, so this is hypotenuse over adjacent. And then we use the Pythagorean theorem. Leg squared plus leg squared is hypotenuse squared. So then this is square root of, let's see, 5 squared plus n squared is x plus 3 quantity squared. So n squared is x squared plus 6x plus 9 minus 25. So n is square root of x squared plus 6x minus 6. 16, I can't read my own writing. Plus 9, not 19. So that would be minus 16. And then we can decode our cosecants and cotangents. So cosecant is reciprocal of sine. Sine is opposite over hypotenuse. So other way around for that guy. And then our friend the cotangent, reciprocal of the tangent. So instead of opposite over adjacent, it's adjacent over the opposite. Then we can do work a little magic here. We have a common denominator, so we can go ahead and write that as one term. So we have x plus 8 upstairs, and we can even factor this guy. X plus 8 under square root, x minus 2 under square root plus c. X plus 8 by itself is the same as root x plus 8 by root x plus 8. So we can sort of cancel one of those and just have root x plus 8 upstairs. Or think of this as to the 2 halves and to the 1 half, we have 1 half then. So then we could expand and say natural log x plus 8. Let's see, 1 half times negative 10 would be negative 5. And then half times negative 10, and then minus a negative, flip the sign. Minus 2 there, plus c. Really, they should be absolute values. Okay, so that's without our friend the partial fractions. Close to the 10-minute mark for that problem. But what if we knew that 50 over x squared plus 6x minus 16 was the same as 5 over x minus 2 minus 5 over x plus 8? Well, if I knew that and started with integral of 50 dx over x squared plus 6x minus 16, then I would call that integral of 5 over x minus 2 minus 5 over x plus 8 times dx. And then I have just a couple simple natural logarithms. So 5 natural log absolute value of x minus 2 minus 5 natural log absolute value of x plus 8 plus some arbitrary constant. A lot faster. So that's what this section is about, is what if we knew this? How do we know that this is true? So how we do that? If we have linear factors, we use A's and B's, linear factors of the denominators. For quadratic, we use AX plus B, CX plus D, etc. And for repeated factors, px plus q to the, say, m power. Use one of them over px plus q to the first, another over px plus q squared, and keep going until you're over the mth guy. So this one, the x squared plus 6x minus 16, that's linear factors in the denominator only. So we're going to use 50 over the factored version, x plus 8 by x minus 2. And we'll say that that's worth a over x plus 8 plus b over x minus 2. So we're saying, okay, if we have these two factors, I can break it into two fractions that have those denominators. Next, we just clear the fractions. We multiply both sides by the LCD, leaving the 50 by itself. Multiplying the first term on the right-hand side by the LCD, the x plus 8s will drop. The x minus 2s will not. Similarly, on that last one, x minus 2 over x minus 2 is 1, but x plus 8 will not drop out. So now we have this thing, a few variables. We get to use a let line. So we're going to say let x equal negative 8. Goodbye to b. Then 50 is a times negative 8 minus 2 is negative 10, plus b times 0. So b times 0 is 0. 50 is worth negative 10a, so a is, there's that negative 5. Notice that was over our x plus 8. We can do the same thing with the b. I like to keep it all on the page, so I'll just finish it up here. This time we're going to let x equal a positive 2. That way now the a is dropping out, but the b stays in the game. So 50 is a times 0 plus b times 10. So 50 is 10b, so b is 5. And that's how we turn the 50 over x squared plus 6x minus 16 into the much easier to integrate negative 5 over x plus 8 plus 5 over x minus 2. Much, much faster and easier to integrate that. All right, so we'll put that to use in a few others. So we turn the long, complicated problems into a little bit easier to manage problems. So next up, we're going to start with an integral of x squared plus x plus 1 all over x cubed plus 6x squared plus 9x. And of course, we're multiplying by dx. So if I want to use partial fractions to make this thing easier, First thing I want to do is factor that denominator as much as I can. So I'll hang on to the numerator. Denominator, I'll pull an x. And then we have x plus 3 and another x plus 3, or x plus 3 squared. So then we're going to let x squared plus x plus 1 over x by x plus 3 quantity squared equal, so we'll start with a over x, one of the linear factors, plus b over x plus 3 to the first, plus c over x plus 3 quantity squared. So when we have repeated factors, you have one of them, then two of them, etc., until you match the exponent. So same rules as before, clear those fractions off. So we multiply everything by x plus 3 squared. So left side we have the x squared plus x plus 1. On the right side, the x plus 3 squared is left. X over x dropped out. In the middle, I didn't have an x at the bottom to cancel the x out, and I was only able to cancel one of the x plus 3's, so the other one is left. And then our last one, the x plus 3 squareds drop, the x does not. So then we figure out, okay, how can I drop some of these out? Well, looking at these two, if I let x equal 0, b and c are going to be gone. So let's start there. Let x equal 0. So 0 squared plus 0 plus 1, left side is now a 1. 0 plus 3 is 3. 3 squared is 9, so I have 9a. 0 times anything is 0. 0 times anything is 0. So a is 1/9. Now, I look at, okay, how can I get rid of some other stuff? Well, let's let x equal -3. That'll drop these two guys out. So if x is -3, we've got then 9 minus 3 plus 1 on the left-hand side. So from our equation where we had already cleared the fraction, -3 plus 3 is 0. 0 squared is 0. A times 0 is 0. Those are gone. B times -3 times 0 is also 0. Those are gone. So we have just equals c times -3. So 9 minus 3, 6 and 1, 7. So 7 is -3c. So c is -7/3. So at this point, then we just select any other unused x and reuse the a and c that we figured out. So let's see, we already used up a 0 for the x, so 1. 1's not bad to work with. So we're going to let x equal 1. Again, we're going back to this line where we have cleared off our fractions. So x is worth 1, so 1 squared is 1, x is 1, then plus 1, 1 and 1 and 1 is 3. Okay, so our a value, a we said was 1/9. So 1/9 by 1 plus 3 is 4, 4 squared is 16. We don't have a b value yet, that stays a variable. X we said was 1, so we have 1 and 4. C, we do have a c value, -7/3, and x is still a 1. So this is going to let us solve for b. Notice everything is a constant except for b. So left-hand side temporarily is a 3, so 3 is worth 16/9 plus 4b minus 7/3. So then we get to b is, that ends up as 8/9. Okay, so this original messy looking fellow here, we can't use just a plain simple U substitution. Trig substitution even would be a little bit on the cumbersome side there. So we're going to rewrite it. We have our a, b, and c. So now this integral becomes a over x. So a was 1/9. So it's this integral of 1 over 9x plus b over x plus 3. b we said was 8/9. And then plus c over x plus 3 squared. C was a negative value, so we'll do a minus. Minus 7 over 3 by x plus 3. Quantity squared, close it up, and multiply by dx. So there, now we're ready to just dive right in and do the antiderivative thing here. First term, we'll factor the 1/9, and antiderivative of 1 over x is natural log absolute value of x. So there's our first term. Second term, again, I'll hang on to this 8/9. And we have antiderivative of 1 over x plus 3. That's just natural log absolute value of x plus 3. Again, we'll hang on to this -7/3. X plus 3 to the -2nd. Antiderivative on that. We would have an x plus 3 to the -1st. I didn't see a -1 out here that I would, so we'll multiply by a -1 there. Derivative of the inside would still be just a 1, so we don't need another factor there. Throw on our plus c at the end there. So we have our 1/9 natural log of x, 8/9 natural log of x plus 3, and then we're just sort of doing the antiderivative of x plus 3 to the -2nd. So x plus 3 then becomes to the -1st. We already sort of factored the -7/3. So we brought a -1 out here. So -1 times -1 is a +1. X plus 3 stays. -1 now to the -2. And then times 1 doesn't really change anything. So really then just a little bit of cleanup on the end there. And that's our antiderivative. Natural log absolute value of x over 9 plus 8 natural log absolute value of x plus 3 all over 9 plus 7 over 3 by x plus 3 plus c. You might see this as 7/3 x plus 3 to the -1st. That's fine too. I don't care which of the two versions you go with on that. So it's a nice way to sort of break things down, make a simpler problem out of something that could have been a little bit more challenging. So next up, we're going to look at what happens if we have a quadratic factor. So we'll do 11x cubed minus 7x squared plus 14x minus 6 times dx all over, and we'll start just factored. X by x minus 1 by x squared plus 3. So x squared plus 3, not factorable over the integers. All right, so this one, they were nice to us. They started off factored. Apparently I'm not as focused as I should be. So we can jump right in with our let line. So we're going to let this 11x cubed minus 7x squared plus 14x minus 6 over our factor denominator. First factor is linear, a over x. Second factor also linear, b over x minus 1. This next factor, though, is quadratic, so we'll have a cx plus d. over x squared plus 3, always 1 degree less in the numerator than the denominator. All right, so we multiply both sides by the LCD. Left side, as usual, that clears it out. We have 11x cubed minus 7x squared plus 14x minus 6. Right-hand side, first fraction, x drops out. So we have a by x minus 1 by x squared plus 3. Middle, x minus 1 drops out, but we still have our x. We still have our x squared plus 3. And the cx plus d, make sure you throw those guys in parentheses. And x squared plus 3 drops, but x and x minus 1 stay. All right. Trouble fitting all that on there. So if I'm after a, notice each of these have x by itself as a factor. So if x is 0, those will drop. So that's exactly where we'll start. Let x equal 0. So left-hand side is now just -6. Right-hand side is a times -1 times +3. The rest drop to 0. So -6 is -3a. So a is a 2. Next, I notice if x is worth 1, the front and the back will drop out, leaving me just the b's. So that's what we'll do next. Let x equal 1. So then I have 11 minus 7 plus 14 minus 6 is worth a times 0 times anything else is 0. In the middle, though, b times 1 times 4. And on the end, something times 0. Those will drop out. So let's see, 11 minus 7 is 4, and 14 minus 6 is 8, 4 and 8. So 12 is 4b. So b is a nice pretty 3. All right, so the only one we haven't gotten to yet is the cx plus d. Notice, unless I go into the complex numbers, I'm not going to be able to drop both a and b at the same time. So we'll just pick some other unused x and keep the a and the b that we've already used. So in this case, it's a and b that we found. Other problems, it'll be a and c that we found. Keep the constants that you've already found. Let's see, we used a 0 and a 1. -1's not bad to work with. So plugging in a -1 here, -11, -7, -14, -6. Trying out the -1, we have a times -2 times 4. And a here was a 2. So my apologies, we will just plug the 2 in. We'll save a step and just plug the 2 in there right away. Then we have plus b. b is a 3. 3 times -1 times 4. My apologies, can't fit all this on the line. C times -1 plus d times -1 times -2. So left-hand side, we get a -38. Right-hand side, let's see, we've got a -16, a -12, and let's see, negative by negative, so plus 2 times minus c plus d. So a little cleanup, and we get -10 is worth -2c plus 2d. So notice we didn't get a single value for c and d just yet. All that means is that we're just going to pick out one more x, some other value of x that we haven't used up yet. We've used 0, 1, -1, 2. 2 will do just fine. Just to have enough room to write, I'm going to start down here. So we will let x equal 2. So plugging 2 into all these will just save you the calculator work. You get to 82 on the left side. So 11 by 8 minus 7 by 4, etc., etc., etc. A we said is 2. X minus 1 is now 2 minus 1, so that's a 1. X is now 2. 2 squared is 4. 4 and 3 is 7. Plus b. B we said is 3. Times x. X we said is 2. Need 2 of those guys. Times x squared plus 3. So 4 and 3 is 7 again. Plus, we don't know what c is worth yet. X, though, is worth 2. We don't know what d is worth yet. Times x is 2. Times x minus 1. 2 minus 1 is 1. So then a little cleanup there. 82 is worth 14 plus 42 plus 2 by 2c plus d. So we get to 13 is worth 2c plus d. So this is a 13, a 1, 3, not a B as in Bravo. So this is just a little 2x2 system. If we just add those guys together, my apologies, I want to try to finish all this. No, we won't finish it on one page. Let me just bring over the 2 pieces of the puzzle that we've got here. So the 2 things that we circled so far, we had -10 was worth -2c plus 2d, and we had 13 is worth 2c plus d. If we just add those together as is, we get 3 is worth 3d, so d is 1. And then we just plug it into either one of those guys. So 13 is worth 2c plus 1. So 12 is 2c, so c is 6. So remember, we had our original integral, we said was the same as a over x plus b over x minus 1 plus cx plus d over x squared plus 3. So we have our a and b values. Our a, remember, was 2, b was a 3, c was a 6, d was a 1. So our original problem, now we can break it into 3 pieces. So the original integral is now 2 over x plus 3 over x minus 1 plus 6x plus 1 over x squared plus 3. All of that times dx. So we can even kind of split this guy up. So integral of 2 over x plus 3 over x minus 1 plus 6x over x squared plus 3 plus 1 over x squared plus 3 quantity times dx. Okay, so the 2 over x is 2 natural log absolute value of x. Similarly with the next guy, 3 natural log absolute value x minus 1. Little u substitution on this guy, your u would be x squared plus 3. du then is 2x. dx, we have a 6. We can kind of break that 6 apart. So I only needed a 2 inside. I'll bring the 3 outside. And then our last one, this is another case where we can use our friend the trig substitution. We're of the form u squared plus a squared. All right, so we hang on to those first couple guys. 2 natural log absolute value of x plus 3 natural log absolute value x minus 1. So this is u on the bottom, du on the top, natural log again. And finally here, our friend, the trig substitution. So we're going to let x equal root 3 tan theta. So derivative of tangent is secant squared, so dx is root 3 secant squared theta d theta. So just this last piece then, integral of dx over x squared plus root 3 squared turns into integral of dx is root 3 secant squared theta d theta. And downstairs, x squared is 3 tangent squared theta. So just squaring both sides of this guy. Root 3 squared is just a 3. So we can pull root 3. We can pull a common factor of 3. Apologies, should have drawn my fraction bar all the way through there. Up top, secant squared theta. Downstairs, tangent squared plus 1 times, of course, d theta. Tangent squared plus 1 is secant squared theta, so top and bottom will cancel out. So we have 1 over root 3 integral d theta. So that is 1 over root 3 times theta. And then we get our original back in. So theta then would be the arctan of x over root 3. And we have our 1 over root 3, or just root 3 down here, plus c. So they still can get a little bit on the messy side. They still can have a little bit of trig substitution, but it does sort of cut down on our work a little bit. All right. Occasionally we do have an improper integral. So we'll do integral of x cubed plus 2x plus 4 all over x squared plus 3